Welcome to The Explainer. Today we're diving into a pretty radical revolution in one of the oldest fields of human thought, logic. We're going to see how the way we actually construct proofs got completely turned on its head, moving away from a few universal laws to building with these modular, almost elegant blueprints. So this slide really gets to the heart of the story. On one side, you have the old way, the axiomatic systems. Think of it like this: a few giant universal laws that are supposed to prove absolutely everything. But on the other side, you've got this new idea, structural systems. Here, every single logical part, every little piece, gets its very own set of instructions. It's a totally different philosophy. Okay, so here's our roadmap for today. We're going to start with that old architectural style, just to see what we're moving away from. Then we'll meet the revolutionary designer who changed the whole game, and we'll get into his core design principles. After that, we'll see how he managed to tackle the really complex challenge of infinity. And finally, we'll look at how all this lets us build custom-made logics today. All right, let's jump in. Right, so first up, from axioms to blueprints. To really get why the new way is so special, we have to understand how things used to be done. Think of early engineering. It could build some amazing things, for sure, but trying to figure out how it all worked on the inside, that was often a total mystery. These early systems, like the ones from the mathematician Hilbert, were kind of like trying to build a skyscraper using only the universal laws of physics and like one type of bolt. That bolt was a rule called modus ponens. Now, the final building stood up, it was sound, but the blueprint was an absolute mess. If you wanted to simplify it, or even just understand why one single connection was holding up, it was almost impossible. Everything was opaque, and that was a huge problem. And that problem brings us to our revolutionary architect, a guy named Gentzen. Back in the 1930s, he did something brilliant. He didn't try to change the fundamental laws of logic. Instead, he came up with a completely new design philosophy, a whole new toolkit. And his big idea? It's actually super simple, but it changes everything. He said that the meaning of any logical piece, like and or if then, is just defined by its rules. You get one rule to introduce it, to build it into your proof, and one rule to eliminate it, to use it or take it apart. That's it. So he gave us two main toolkits to do this. First, there's natural deduction. This is awesome because it works a lot like how we humans actually think. You can make temporary assumptions, kind of like putting up temporary scaffolding while you build, just to see where an idea leads. The other toolkit is secant calculus. This is much more like a detailed engineering schematic. It shows the precise step-by-step relationship between what you know and what you can conclude from it. But, for any modular system to work, you need some ground rules to make sure all the different parts actually fit together. And that brings us to the really elegant part of the design, the rules of harmony. So, the most important principle here is called harmony, and it's a simple idea. The rule you use to build something, the introduction rule, has to be in perfect balance with the rule you use to take it apart, the elimination rule. What you build up, you should be able to cleanly take down and nothing more. It's all about that perfect balance. And this right here is a perfect example of what happens when you ignore harmony. A philosopher once invented this junk logical piece called tunk. Its introduction rule was way too generous, and its elimination rule was way too powerful. The mismatch completely broke the system. You could prove literally anything, that 2 + 2 is 5, that the sky is purple, anything you want. It was total logical chaos, and it's the perfect demonstration of why that harmony is so important. Okay, so once you have these nice, harmonious parts, you can start to optimize your blueprints. And that process is called normalization. It's basically about finding any pointless detours in your proof, like places where you build something up just to immediately take it apart again, and just cutting out that redundant step.
And this illustrates it perfectly. You start with a proof that takes this winding, inefficient route to get from A to B. Then you apply normalization. You spot that detour, and you get rid of it. And what you're left with is the direct, canonical proof, the straightest, most elegant line from what you started with to your conclusion.
Now, Gensen's absolute masterpiece was his cut-elimination theorem. See, in older systems, there was this powerful shortcut called the cut rule. You can think of it like a leap of faith in the middle of a proof. It let you jump to a conclusion without showing all the little steps in between. It worked, but you couldn't see how it worked. Gentzen proved you could get rid of every single one of those cuts from any proof, and you wouldn't lose any of the system's power. It was incredible. So why does that matter so much? Well, when you eliminate the cut rule, you're left with what's called an analytic proof. And that just means every single step is transparent. Everything in your conclusion was already hiding somewhere in your starting points. And that transparency is the absolute foundation for how we get computers to automatically check proofs for us today.
Okay, so this whole modular system sounds fantastic for simple statements, but what happens when we need to talk about all things or some things? Concepts that have to deal with a potentially infinite number of possibilities. How do you handle that?
Well, this is where we have to design some really specialized components. We need rules specifically for quantifiers, the tools we use to manage infinity. Right, so the rules for quantifiers like for all and there exists, they're like special load-bearing columns in your design. To prove something is true for all numbers, you can't check every number one by one. Instead, you use a temporary placeholder, a variable. But you have to be so careful about how you use it. It has to follow these really strict locality conditions to make sure it's truly a stand-in for any number and not just some specific one. If you mess that up, the whole structure comes crashing down. And all of this brings us to the modern legacy of Gensen's revolution, the ability to not just use logic, but to actually design it. This is where it gets really wild. Today, proof theorists can take a fundamental truth from a totally different field, say an axiom from mathematics, and they have a systematic way to convert it into its own custom set of harmonious introduction and elimination rules. So you can literally take a standalone law from somewhere else, run it through this process to turn it into a new, well-behaved inference rule, and then just plug that new component right into your logical blueprints, and it's going to work perfectly with all the other parts. I mean, this is just incredibly powerful. It means we can build custom, bespoke logical systems that are perfectly tailored for a specific problem, whether that's in computer science or linguistics or philosophy. And we can do it while guaranteeing that the new system is still analytic, still transparent, and still easy to verify. So let's just recap. We've seen this fundamental shift in how we think about logic, right? We moved from these rigid, opaque systems to a flexible, powerful design methodology, all thanks to Gentzen. We now see proofs as these transparent, modular structures built from parts that each have their own clear, simple instructions. And this all leaves us with a final big question. Gensen's revolution gave us the tools to literally engineer logic itself. So if we can now design the very blueprints for how we reason, what new structures of thought are we going to build next?